Thank you, Mark. So, what I want to talk about today is cyber-physical systems. Right? I've been talking about cyber-physical systems for a few years, and the first few times people didn't know what it was. I think that the term now has percolated several communities, but loosely, cyber-physical system referred to the intersection of different domains, control, communication, and computing, to address modeling, design, and analysis issues in physical systems. From it's a intellectual paradigm which I think is useful to again to model, analyze, and design systems which have been in particular infrastructures that have been heavily in which the sensing, control, and communication has been heavily embedded. I'm talking about smart grids, for instance. I'm talking about smart buildings, smart transportation systems. Technology push is there. Now we can and we are embedding sensing, actuation technologies in these large infrastructures, and this is changing the way we look at them, because there's lots of new opportunities that come with that to provide efficiency, safety, and comfort, depending on the type of infrastructures, right? So what's different? I think the cyber-physical systems, we have been doing it for quite a while. You can claim that as soon as we had a computer, we had a cyber-physical system. Any digitally controlled system, you can see a cyber-physical system. What is different now, I think, is that the systems are so large that it's difficult to use what we have been exploiting the past few years, which was separation of concerns, right? When we're designing a control system, we put the communication infrastructure dedicated, the computing infrastructure which was dedicated, and it was designed in such a way they could be abstracted away because they did not affect the actual working of the system. I'll give you just an example. In a undergraduate control lab, you have an inverted pendulum, right? To control, you use a computer, use serial cables, perhaps, to link sensors to the computer and to the actuators. And this the communication and the computing infrastructure is dedicated to it. You design in such a way that you have enough bandwidth to communicate, and that you have enough computing power to do all the computation of estimation and control algorithms. Therefore, you can abstract it away and focus on the control problem at hand. If you have, let's say, large infrastructures, then you're going to have to use general purpose networking. You do that because you want to piggyback on existing infrastructure, take Wi-Fi in buildings, for instance, and also because using off-the-shelf component costs less. You cannot afford to have a dedicated communication infrastructure for any of these applications. And so I think the separation of concerns does not apply anymore. There's a coupling between the computing, the communication, and the control infrastructure, right? And therefore there's need to do co-design. And cyber-physical systems are, I think, the modeling paradigm to do this co-design. Another issue that we have is scale, right? We're not talking about one small system, a controller, and a few sensors. So we are potentially talking about thousands, tens, or hundreds of thousands of components. So what are the issues here is, I think modeling is an issue. There's now a big talk and push toward urban system, resilient urban system, interconnected infrastructure, water, power, transportation. We don't even know how they work, how do they interact. So creating models of them, I think it's a big issue. And in terms of design, I think the main concerns have to do with the robustness of design or resilience. The two terms, although different, are used interchangeably, and security and privacy. You've heard about privacy yesterday, and So the research direction that I'm pursuing is, the issue of sensor selection, sensor scheduling. You're going from having too little information about your infrastructure to having too much, right? If you want to make a decision, it's infeasible and useless to collect all the information and make a decision upon them. There's relevant information and irrelevant information, and understanding which is which, depending on the question that you're asking, I think it's an important issue to address. And that's what I'm going to focus on, is having attacker into physical in cyber physical systems, and addressing the issue of an attacker that wants to. There are several entry points, not just the cyber part of the system, but also the physical part of the system, and whose goal is actually to affect the operation of the physical system. So one of the first questions is the security of a CPS an issue, right? If we have good cyber security, is that sufficient? Right. I claim that there is a distinction between cybersecurity and CPS security, and I think the main difference is the presence of a physical system. Dealing with physical systems introduces some new challenges. When we talk about security to apply to physical infrastructure, we really talk about safety, about resilience, and so not necessarily want to. Our goal is not to protect the information system and guarantee availability, integrity. Of data, but that could be a tool. But really, what we want to protect is the physical system. Also, when you deal with physical system, there's an issue of inertia that is not as visible and as present in pure cyber system, right? If you realize the computer is compromised, you turn it off, right, and then you deal with it. If you have a physical infrastructure, like an airplane that is flying, that you realize has been compromised, right? You don't have the luxury of just turning the system off, troubleshooting, and then bringing it back on. You have to continue operating under attack. Guaranteeing what we call graceful degradation. You remove certain ancillary services, but you want to guarantee the main one, for instance, the plane flies safely. Also, patches might be more expensive in the physical world. I think with challenges, fortunately, there are all sorts of opportunities as well. And the physical systems have the luxury of following very precise physical laws, for which we have good models, right? You can use the predictive power of these models to infer something about the system, whether the system is operating correctly or not. And so what I advocate is to use models and their good predictive power to develop tools which are system theoretic tools to address the issue of security in cyber physical systems. So today, I just want to touch on a small part of the research that I do, and on the use of the physics of the system to be able to detect integrity attacks on sensors and actuators, okay, in my cyber physical system. Let me just give you a quick example, which is the usual one, Stuxnet. Okay, if you remember Stuxnet, as David Sanger says, he had two components, right? One was designed to send the centrifuges out of control, so to exert control on the system, right? And the other, which affected more the cyber part, was corrupt the sensor measurement, so that the operators in the SCADA master would see normal operation, therefore would not intervene, while instead the centrifuges were spinning at high and low speed, so as to break them, rather than spinning at a constant speed, which is what the SCADA master was seeing. Okay, so an attack like this so what we did is, let's take a model. Let's try to model this attack and the system together and see why the attack was successful. So that's what we did. And so we need a system model, and we picked the easiest that we can. Right? It's a very simple dynamical model where x is the state, could be the angular position and velocity, the two states of my centrifuges. And the equation above tells you how the system evolves in time, right? And then you equip it with sensors, right? Could be motion sensors, which is this yk, which it measures some function of the state, either directly, position and velocity, or some function of it, with some noise. Okay. So then a physical system is equipped usually with 2 or 3 algorithms. One is an estimator, takes the measurements and maps them into an estimate of the state. Very standard, so Kalman filter is used very commonly in industry. And a controller, so that feedback controller that takes the estimated state and designs a control input so as to regulate let's say with the centrifuges, to spin at a constant speed, for instance. Here we're going to equip it with an LQG controller. It's just an optimal control strategy that you can find in books. This is all technology at this point. So this optimal control tries to achieve the control goal without using too much energy, by minimizing. So it's a quadratic function of the state and of my input. The third piece is a so-called failure detector. It's something that measures the discrepancy between what I measure and what I am supposed to measure, right, according to my model. I expect the system to be at a certain point, and I measure. I take this discrepancy, I square it, and I weight it appropriately according to the noise, my sensor noise, and I build this detector. It's called the chi-square detector. It's very widely used. And I use this quadratic function. I set a threshold. There's methods that you can find in books. This threshold, you set it based on the desired false alarm rate. You don't want it too high because then you have to go and check false alarms all the time. So you set that, and then you can design your detector as GK. And again, this ZK is YK minus the predicted, so it's the output minus the predicted output, right? If there's too much, if the discrepancy is too high, then GK will go above the threshold and will raise an alarm, right? And this really tells you, and because there's a discrepancy between what you measure and what you're supposed to measure, so either the sensors are telling you the wrong things, or perhaps the model is not adequate anymore because some accident has happened, okay? So it doesn't pinpoint what happened, but it tells you there's an anomaly there, okay? And this is what systems are equipped with, even with less sophisticated systems sometimes. Okay, now let's model the attack. So the attacker could record all measurements and could inject malicious control input, right? So we'll call this a replay attack, although it's not a replay attack as known in the cybersecurity community. So you record, you record a sufficient number of outputs, so to know how the system in steady state is operating, and then you just replay it while you're injecting your malicious control input, and that's pretty much what Stuxnet did. Okay, so the difference is that now you have equations, so you can analyze what happens when this attack kicks in. And it's really a good paradigm, not just for Stuxnet, but for SCADA system, where you have a bunch of control loops which are remote, so you cannot check right away. So you need you have remote sensors, and you have then a SCADA master which oversees the operation and receives the sensor readings from these remote locations. It has to make sense of them. So it will be easy, especially as SCADA moves from a closed system to an open system, where you're using wireless. Wireless HART is a It's a new standard. You use Ethernet, so it would be possible for an attacker. So in Stuxnet, none of this was used. Actually, it was a USB, probably, that corrupted the system. It can get in the middle, take the faithful measurements and just modify them, and so that it sends to the SCADA master forged sensor measurement to induce it to believe whatever it wants to believe, whatever the attacker wants the system to believe. So if we run the system that we modeled, and let's see what happens to my detector. My detector is what is going to tell me whether something is wrong or not. And this is just an example, scalar example, so I can plot it. You can see that this measures the detection rate over time. And for this particular system, when the attack starts at time zero, this replay attack, that the detection rate is 5%, which was my false alarm rate. So that means that the detector is useless, cannot detect the attack. So why? So we knew that. We had an existence proof, which was Stuxnet. Why does that happen? And so what I need to do is look at my detector, and if I look at it, remember the detector was a quadratic function of this term, which is we call it innovation. The difference is a discrepancy between what you measure and what you expect to measure, right? And under attack, this is the innovation under replay is the same as the one without the replay, plus a term which evolves according to this matrix A to the K. Okay. So this matrix is nothing but a function of my system. A, B, C are my dynamical system parameters. And upon the controller, this is the gain of the controller L, and the gain of the estimator K. Right? So if we go back to it, if this matrix is stable, right, all the eigenvalues are within the unit circle, this goes to 0. Right? If this goes to 0, then the innovation under replay will look exactly as the innovation without replay, and that's why we cannot detect such an attack. So if this is unstable instead, then very soon you will be able to detect the attack. The fact is that in most of the cases, this matrix turns out to be stable, so it doesn't work to our advantage, right? And that was in Stuxnet as well. So what would you do, right, in this case? So we'll do what many people thought about doing. It's it's a natural. So what you could do, you could run software attestation on these sensors, right? See whether somebody changed the code on these sensors, right? And that's something that is probably useful to do, right? What I want to propose is actually use the physics of the system to authenticate whether sensors are telling me the right things or not. And what I'm going to do is this physical watermarking. So let's say that the output, the measurement, with the optimal inputs, the one that were designed for performance and solely for performance, look like this. Let's say it's an image, right? So in addition to my optimal input, right, which since it's which an attacker could infer because it's textbook stuff, I will add a random input, right, which I call watermark signal. And with that, I will get a watermarked version of my output once it goes through the physics of the system, right? And then I will run that through my detector, and I should be able to recover my watermark or the effect of my watermark, right? And if I do, then I know that the sensor is telling me the right thing. If I don't, I'll get, let's say, white noise, as was the sensor measurement noise, for instance. Then there might be a problem. Okay. So again, if we model this, we'll see that what happens to my innovation. Remember, this was the basis for my detector. It was, again, the same. The innovation under replay was the same as the innovation without the replay, plus this term that goes to zero, that might go to zero, plus something that depends upon my perturbation. Okay, and if I do that, I'll put my perturbation to be zero mean. I don't want to drift the system from its desired. I just want to perturb it around its desired operating point. And if I do that, and I use some variance to my random signal, and as I increase the variance, this is again a scalar case, then my detection rate increases. Okay, so if I perturb the system, the more I perturb the system, the easier it will be to spot actually the presence of the attack. The problem with that is that I'm acting on the system. By acting on the system, I'm expending energy, and I'm also not controlling very finely the system anymore. So I'm paying for it. I'm paying performance. And there's a very nice trade-off, because the more I perturb the system, the higher will be my detection rate, but the lower will be my performance. And for the case of LQG, where we have a very specific cost function, then we can quantify this trade-off, and we see that it's linear with the perturbation, with the energy of the perturbation, which will be the covariance matrix, right? So the optimal cost is penalized by linearly in Q. Okay. So what you can do is, now you have some design goal, you can design this Q, right? And as a first order approximation, I will design my perturbation process to be IID, so no correlation, just because it's simpler, right? And I have to decide my Q, Z is zero mean, and then I have to decide my covariance. And the way you design covariance, you ride this, you exploit this trade-off. You say, I want to constrain my performance loss. I don't want my performance to go below a certain level. But with that constraint, I want to maximize my detection rate. Now, detection rate is not something you can compute, but you can find a function which is monotonic with it, which is delta GK. Or you can do the dual. I want to constrain my increase in the expectation of GK. So I want to constrain, I want my detection rate to be at least this much, and I want to have maximum performance given that constraint. They are the dual of each other, so you can solve either. Turns out that being a linear problem, you can separate the problem in designing first the form of Q, it's a matrix, and then you can turn the knob and decide the norm of it. So if you just work on the form of it, of my covariance matrix, you see that it's worth doing this optimization, because you can get, this is just an example, a 10-fold increase in detection rate with the same constraint on performance. Okay. So it's and then it's actually very nice for design. Once you have the form of Q, then you can decide what ROC curve you want to achieve. Mindful that the optimal point would be the top left corner, where you have 0 false alarm rate and 1 detection rate. But that happens by turning up the norm of Q. But when you turn up the norm of Q, you pay in performance again. Okay, but it's a good engineering tool, right? You can use it. It's just 2 knobs. You don't need to know much of the theory behind it. So if you use non-IID, can you do even better? It's expected to do better, because you would like to have IID at the output, not at the input. So if we do that, then we can see that, and again, this is the ROC curve, where you have false alarm versus detection probability. And if you compare the IID case, which is the blue one, with the optimal non-IID, which is the red one, then you get an increase in performance. But if you're an engineer and you look at this curve, you say, well, it's pretty much the same, I don't care, right? The thing is that when you design detectors, you don't care about being on the right part of the plot. You really want to be on the left part, because you want very low probability of very low probability of false alarm. So if you zoom in into the bottom left corner, then you will see that the improvements over IID can be of could be 2x, for instance. So and that's where you want to be. We were before, in my examples, I was at 5% false alarm rate, which is reasonable, which still gives you a 40% increase in detection performance. Let me give you an example, okay, so of how this would operate. And again, let me take also the chemical plant. I always use the chemical plant because it's the only real world example of a system for which we have a decent, realistic model, okay? And I understand that this is, realistic models go well beyond academic ones. This is the Tennis Eastman plant, so it was written in Fortran. We took the pain of converting the Fortran into MATLAB. We took the nonlinear equations, we linearized them, we discretized them, so we did everything by the book. And then we designed the controller, very simple controller. Actually, we designed two controllers. Right? To the left is the design that every control person would design before they were concerned about security, just for performance. And you see that if I attack, so on the top left you have in blue is my detection function, in red is my threshold, and in the middle one you have the attack, which starts at time 15. And you will see that although the replay attacks occurs, then the detection is never triggered, so it's useless. If I use my authentication signal, then you can see that the detector function just jumps up and detects the attack right away. One more thing that I wanted to add is that I think using the physics of the system to authenticate shelters you from remote attacks. Because he would have to change the physics of the system in order to alter this detection scheme. So I think it's quite robust, and it's a complementary scheme. I'm not saying that it should be used in alternative to all the different in detection intrusion scheme, but I think it's a nice paradigm that could be used in addition to it. And so going back to Stuxnet, the funny thing is that actually we came up with a model. Although I used the Stuxnet for motivation, we came up with the model and with the solution to the problem a couple of years before Stuxnet started, which was great for me because before people would ask me, so you dreamed about this? And I said, no, I watched a lot of movies like Ocean 11, and which was not a good answer for them. And now I do have an answer after the fact. Okay, I'm going to conclude here. Thank you.
Any questions for Anthony?
Bruno.
Oh, sorry, Bruno.
It's okay. We are interchangeable at times. At least when we bike.
That's not true at all.
When we bike, sometimes. Yeah.
So, when we deal with this problem, we sort of look at the differences between the general state of large enterprises and anything that is a sensor is treated equally. But then you get to the nuances of specifics like electrical or gas and oil, and then the specific sensors, of course, have different impacts. So. And sometimes we monitor like the non-sensors, just voltage levels that aren't part of the integrated sensor environment. And then we look at, maybe we use wavelet transforms and things to look at some anomalous behaviors that aren't really anticipated. So, so I'm not quite sure how to articulate the question, but if you have a full understanding of all the sensors in a network, and then maybe you're ignoring, or not ignoring intentionally, but there's other opportunities to take disparate pieces of information and treat them as sensors, how does that affect your analysis?
So, all additional information, right, would be sensors, right? If they are independent from what you're measuring, they are sensors. So, therefore, you will have to take into account in this specific model, right? I assume that I am gaining advantage over all the observables, right? So your paradigm would not fit this model. But I don't have time to go over it. It's actually the next few slides. So if you have a subset of the sensors, then it really matters. Yeah. Then there's a totally different analysis that you can do, and we've actually done that. And it really depends which sensors at that point. Which sensor you should corrupt, which one you should not corrupt. and what kind of perturbation you can induce. In most of the cases, the perturbation you can induce is bounded, because you will have to perturb the system in such a way that these sensors you have no control over, right, are not affected too much. Right? Because if they are, then they will raise an alarm. Right? And there are specific cases where even if you are only observing a subset of the sensor, you will be still able to send the system unstable. And the way you'll do that, you will render the unstable states unobservable even to the good sensors. It gets a little technical, right? But this depends on the system. You cannot do it on every system. Basically, you'll make the part that you want to render unstable unobservable with the sensor that you have hijacked, so that the ones that you don't own are not going to be able to see that part of the system, right? And you can do analysis over it, right? And if you have a good model of it. If you don't, then all bets are off.